welcome to this talk. I'm going to talk about Java 8 stream performance. Thank you for coming. And I'd also like to say thank you to the organisers of the conference for inviting me. Can I ask how many people came to my talk yesterday? Wow, you guys really don't learn from experience, do you? Yeah. That's quite. Oh, I'm kind of flattered, actually. So that means I have to run really quickly over the jokes at the beginning where I introduce myself, and they're pretty lame anyway. So this is me. This is for the people who weren't there yesterday, and these are the programs that I'm a member of, managed by Oracle to build the Java community. This is the what I'm probably known for, if I'm known at all in the Java world, as the co-author of what I like to call the best book on Java generics, bar none. I'm really confident of that, absolutely. There's only one. And also author of something that I can't make the same claim about because there's actually lots of books on Java 8. But I wrote this book on Lambdas. I can actually claim that maybe it isn't the best, but it is the last. It was the last. And I'm also the maintainer of the Lambda FAQ, which is a bit neglected at the moment because of the pressure of writing the book, but I'm hoping to get back to it. And I found something, for the people who were here yesterday, I found something new to say about myself. I discovered a slide in which I showed the first computer I ever used. So we thought this was pretty good at the time. It was embedded in a large spectrometer, so it wasn't really a freestanding computer, but I thought it was okay. That was under 2 microsecond memory cycle. Yeah, 16-bit words. Yeah, it was good stuff. It was good stuff. And you know, frankly, I don't really think. I think we knew it all then. I don't think we really learnt anything new since. So the agenda for today's talk is I'm going to talk a lot about, well, some about the background. I'm going to very, very, very brief one-slide introduction to streams in Java 8. I won't ask whether people have used them because I'm not really going to depend on that. You'll get enough of a feel for them, I hope, to understand the talk, even if you're not familiar with streams. I'm going to talk a little bit about parallelism, but everybody knows about that. I'm going to read you a short sermon on the subject of microbenchmarking, which is kind of compulsory for a performance talk. And in fact, this whole talk is a bit of a sermon, really. I thought it's a bit like a kind of... it struck me that it was a bit like a bad sex education talk in school, because like I'm going to tell you, you've come here to hear the interesting bits, and I'm going to tell you all the reasons why you shouldn't be doing this, why you shouldn't be interested in it, and why you shouldn't be doing it. I'm going to keep on saying, this is why you shouldn't be interested in performance. So everyone just goes away and takes the same practical interest in the subject, regardless of what the teacher says. So, following this agenda then, the first question is, why are we interested in streams? And here's my 2-slide background on why we're interested in streams. It's to bring a functional style to Java so that we're going to get better code. And there is also the added bonus that streams will enable you to exploit hardware parallelism. And the slogan that they used was explicit but unobtrusive. So I'm going to explain, you'll see in a moment what that means in practice. The intention was to, the primary use case for streams in Java from now on is going to be the replacing of iteration over loops with, for aggregate operations. So instead of writing something like this, my example here has there's a data type called people, with attributes of city and name, I think, and age. But here I'm just using the city that they live in. So I'm imagining I've got a list of person here, and I'm going to iterate over this list of person. For each one, I'm going to get the city, and I'm going to filter the name of the city over to see whether it's less than 4 characters, and then and if it is, I'm going to add it to a set. And actually, I made a mistake there because when the Stream API was being introduced, when Brian Getz was introducing the Stream API at all the big conferences a couple of years back, he would put up a slide like this and a piece of code like this, and he would say to people, can you figure out what this is doing? And after about 3 seconds, he'd say, okay, you failed. Because the equivalent is going to look like this now. And even if this looks unfamiliar to you, I guarantee that within a couple of weeks of starting to use this kind of code, you will be able to understand it in less than 3 seconds. There's a big advantage to it. So here what we're saying is we're going to take the list of people, we're going to put it into a stream. We're going to map that stream is like, I described it yesterday as being like data in motion. It's a dynamic data structure. It never actually holds variables in values statically. They're always in motion when they're going into a stream. So that we're now feeding the elements of the collection into the stream here. We're mapping each element of the stream to the corresponding city using the get city method of person. We're then filtering it over the same predicate as we used before, this truth-valued function which says whether the string is has less than 4 characters or not. And then we're going to collect the terminal operation on the stream. This launches the stream, and this collects up the elements at the end of it, and we're going to put them into a set. And the claim is that this code is going to be, once you get used to it, it's more concise, it's more readable. Because we're using lambdas, which are a much more abstract way of expressing functions than the clunky anonymous inner classes that we used to have to work with, the operations are much more composable. We get much more fine-grained APIs. And, as a bonus, it's parallelizable. So here all I've done, in order to make this into a parallel stream, all I needed to do was to replace stream here with parallel stream. And hey, we're going to get all the benefits of parallelism. Well, maybe. We'll get some of we can get some of the benefits of parallelism. So the practical benefits of streams are that the functional style that I showed you there is going to affect all collection processing. This is the future of collection processing in Java, and it's going to be a lot better. In some cases, going parallel, in certain situations, will improve performance, possibly. But I have to talk about it because everyone cares about performance. I'm going to tell you why you shouldn't, but you're still going to care about performance. Everyone always does. Why are we interested in parallelism? Well, this slide is good. This slide's a kind of pretty familiar one now. This slide, the picture here originates from a very, very famous article called The Free Lunch is Over by Herb Sutter, which actually appeared, I looked it up, in 2005. So this has been known about for a long time. The limitations on what was going to happen to hardware has been known about now for 10 years. And as you can see, the green graph here, the green line there, on a logarithmic scale is the number of transistors on Intel chips. And it just increases exponentially from the early 1970s and shows no signs of slowing now. Whereas the clock speed, as you know, leveled off in the early 2000s, the early 2000s, and isn't going to speed up again. So the way I like to think of it is that when the microchip was born, there was a good fairy and a wicked fairy at its shoulder, one each at its shoulder. So the good fairy was Gordon Moore, and Moore's law has held to this day. And this is a kind of the gift that keeps on giving to us. We'll learn who the wicked fairy was before very long. In 1965, Moore predicted that this would happen, and it's gone beyond his wildest predictions. Still, what are we? 50 years later, it still holds. So this is what a modern microchip looks like now. This is a workstation, an Intel workstation chip, about 2 years old. 10 cores in this one. You can see them along the top here, and this stuff in the middle is level 3 cache. And you can see there's a lot of it, and there's more cache still in the adjacent to the cores. So we've got 10 cores now, and we're going to have a lot more soon. We already actually have a lot more, because of course all of our computers have got GPUs in them, which are massively parallel. We just haven't found out how to use them yet. So there's really so the proposition is we have to get ready for a world in which there's going to be a lot of spare hardware that we don't really know how to use yet. So that's what the explicit but unobtrusive parallelism of streams is about. Can we find a way of automatically taking Java programs and parallelizing them? We're not like vendors of kind of big video editing suites, who of course are busy rewriting their software to make sure that they can, on platform-specific ways, to make sure they make use of all of the cores. They can do that. We can't do that as Java programmers. We have to rely on the JVM to distribute our work over, in this case, over 10 cores. That's going to be pretty tough. So the last preliminary that I want to discuss before I go on to actually look at the case study is microbenchmarking, because if we want to know whether or not we have actually succeeded in achieving anything when we go parallel, which is going to be a major theme of this talk, we need to be able to measure the results, and this is really hard to do. It's really hard. That's in bold. I meant it to be in italics. It's really hard to get meaningful results from a dynamic runtime. What we would like to do, ideally, of course, would be to take our application and to run it in the production environment with something like A/B testing, the way that internet marketers think of it. In other words, with the code that's running in parallel and the sequential code, and compare the performance in a real life system. That's really hard to do, of course, because getting measurements from production systems isn't easy, and making sure that they've got like typical loads and the network conditions are controlled and all this kind of thing. It's very hard to do. So we end up micro-benchmarking because that's much easier. You can do that on your desktop. And the idea then is, instead of, we can eliminate the influence of all these environmental variables, the load, the network environment, how the database is performing, yada, yada, yada. We can eliminate all of those by running controlled experiments, by running exactly the same, our A/B alternatives within an environment in which all this stuff is controlled. And then it turns out that controlling the environment of our code, as it were, is extremely hard, even on the desktop. And the main reason for that is because a dynamic runtime, like the JVM, they're now just so clever. I mean, partly the timing methods are flawed, so to start off with, you're in trouble. You can't actually measure what the time is. System current time millis has very poor granularity, and system nanotime is very dependent on the platform that you're on. But worse than that, even if you could measure them accurately, you don't really know what's going on inside of your program. You know what byte code's being executed, but what's the machine code that's being executed? Well, you don't know, because halfway through your run, the hotspot compiler will kick in, and it will compile what has previously been interpreted. And then it'll do some garbage collection. And then it's been profiling your code for a while, and it decides to optimize it. And then something happens, new classes are loaded, or a different thread accesses a lock, and it de-optimizes it. And all of this affects your measurements in a very, very unpredictable way. It's really, really hard to make use of it. The worst optimization of all, in my opinion, is dead code. It's kind of a weird thing to say, the worst optimization. Right? This stuff is very clever, and it has a huge effect on the performance of Java code. This is why Java code is so competitive. And I'm complaining about it. So the worst optimization of all is dead code elimination. So you need to calculate your results, because if you're going to provide a representative CPU load, and yet what are you going to do with those results? That's really hard. That's really hard to work out. You're going to print them to the console? That's going to take so much time. It's going to completely destroy your experiment. It's a real problem knowing what to do with them. So you say, well, I won't do anything with them. Well, if you don't do anything with your results, the compiler will be able to tell that you've not done anything with your results, and it will eliminate that dead code. So you'll end up running an empty loop. So this is tough stuff. It really is. And you quite often see in people's blog posts, you see, hey, I ran this benchmark, and they call system current time millis, and then they do some work, and then they call system current time millis again. And usually, I'm sorry to say, those benchmarks aren't worth very much at all. So a very strong piece of guidance that I would give you here is, don't try to eliminate these effects yourself. As far as I'm concerned, much cleverer people than me have thought about this, and they've encapsulated their results in benchmarking libraries. Google Caliper is one. The one that I use is a Java benchmarking harness, which is actually produced by Oracle guys who know a lot about the JVM. And if you learn about the Java benchmarking harness, that was my choice, and use that consistently, you're much more likely to get realistic results. It's still not good enough. You still have a lot of problems with statistical outliers, and you have to think carefully about whether your results are statistically meaningful. And even then, you'll still have made mistakes, and you really need to get your benchmarks peer reviewed. It's not really a minor matter trying to measure the performance of code. So that's the sermon I was going to. I wanted to read to you about this, and now I want to go on and look at the case study that we're going to examine today. So the case, the one I've chosen was an example out of the book. I decided that just for the sake of demonstrating what you could do with streams, I would try to reproduce in Java the various options of grep. A lot of these are kind of not very challenging because grep can do things like it can put the name of the file in front of the output line, or it can not do that and that kind of thing. But the one that made me hesitate a bit longer was grep-b. I'm not used to this one. Grep-b, the man page for that says that the offset in bytes of a matched pattern is displayed in front of the matched line. So you can scratch your head and think, well, wait a minute, I can easily see how to do this if I have an accumulator. So you read in a line, you get the length of the line, you know what the displacement of the next line is going to be. But it's a bit more of a challenge to work out how are you going to do this if you aren't allowed accumulators. So the people who were here yesterday will know that my big sermon yesterday was we aren't allowed accumulators any longer because they're not compatible with running processing our code in parallel threads. Because the accumulators will require, because the parallel threads will require to simultaneously access the accumulator, and you're going to need to mutually exclude them from that, and then they're going to be standing idle a lot of the time. So we've got to try and think of a solution for grep-b that doesn't involve an accumulator. So here's the example that I'm going to demonstrate it on. This is a quatrain from the Rubaiyat of Omar Khayyam. The moving finger writes, and having writ moves on, nor all thy piety nor wit shall bring it back to cancel half a line, nor all thy tears wash out a word of it. That's profound. Omar Khayyam, it turns out, I read this in Wikipedia yesterday, as it was an 11th century Persian mathematician, astronomer, philosopher, and poet. He also wrote treatises on mechanics, geography, mineralogy, music, and Islamic theology. And, sorry, excuse me. And in his spare time, what a killer for a punchline. I was going to say, in his spare time. I'm so excited about my joke. In his spare time, he thought about immutability. I got it out. So, if we run grep-b on that text, this is what we get out. I've chosen an arbitrary pattern to match. Uppercase W followed by anything followed by T. So that'll match the second line, which has the word wit in it, and it'll match the fourth line, which has a W here and a T at the end. And it will tell you the displacement, the byte displacement within the text of these two lines. So I'm going to tell you, so we're going to look at the performance of this, and I'm going to start off by saying that we shouldn't care about it. So my sermon continues. Why shouldn't we care about it? Well, maybe we shouldn't care about it because we don't have a problem. How would we know if we had a problem with the performance of our hypothetical program for grep-b? Pardon?
I would just say maybe it feels slow.
Sorry, maybe it just feels slow. There lies the road to ruin. If you think it just feels slow, you're going to tune it, and then it's going to feel a little bit less slow. So, well, maybe we'll tune it some more, and so on. So this is a problem that programmers have about understanding performance. Is we think that what it's about is getting things precisely right. We're going to get our program just as efficient as it can be.
What path is it shutting you off? Where, what this constraint, and it's a constraint we're dealing with. What does it prevent you from doing?
Well, yeah, that's a kind of that. I should repeat the answer. It was like what constraint is the slowness of the program breaking? Okay, that's actually
what path does that? What is it you want to do that constraint is preventing.
Yeah. Okay. So if I can make that a little bit more abstract, I'll say, if you don't know, I mean, if you haven't decided in advance what it is, what performance you want from your program, if you don't have a target for it, then tuning it, then deciding that it's too slow and trying to tune it is just a path that you're never going to get to the end of. So the first thing to say is, you don't have a problem unless you have a performance target. Okay, so maybe you do have a performance target. You still shouldn't care about the performance of your stream code. Why shouldn't you care about it? Maybe there's a problem, but do we know whether the problem's in our process or not? Let's have a look at an example. I fixed up an example which was going to demonstrate a program that runs really badly, but that we shouldn't care about the performance of it. So it's not that one. Let's see. This is the stuff I don't do very well. Okay, so here's a program called Not Your Process, and I'm going to run this. I gave the game away there accidentally. So I run this, and this actually does implement grep -b, Not Your Process, and it runs. You can't tell how fast it's running, but I'll show you what I'm seeing if I look at the. Oh, that would be a good idea, wouldn't it? This is not my. This is not my forte, but I'm trying to get used to it. Here we are, mirror displays. How would that be? Okay, so I didn't really give the game away, you didn't see. Okay, so I'm running this program which is called Not Your Process, and it's processing a big file. I can't remember how many millions of lines. And it's going to, let's suppose that it's going too slowly. Here's a reason why it might be going too slowly. Oh, there was a reason why it was going too slowly, but it's gone now. I shouldn't, okay, Not Your Process. Okay, all right, now we're seeing something that we really would prefer not to see. So either using Process Monitor or whatever Windows has as the equivalent of this, or VMstat or something similar on Unix machines, you're going to, by one means or another, you can find out where the processor time is going. In this case, the red is kernel time, and the green is is time spent in user space. The red here should be about 10% of the total CPU usage. So something's going on there. I mean, this is the first question you should ask yourself if your program isn't performing very well, is where is it spending its time? And if the system as a whole is spending its time with the operating system doing all the work, then you've got something seriously the matter. In this case, what's seriously the matter is something that I just fixed up to do. I faked the program so that, in fact, the input is from a file input stream, which is unbuffered. So the operating system is spending all of its time picking up one character at a time off the disk. Okay, that's an extreme case, of course. You're not really going to have that, but it may well be that you've got some network problem or whatever that is going to mean that the operating system is spending its time. It may be swapping, it may be swapping threads, context switching. It may be I/O. It may be the network. But the first thing to check is it actually your process that's the problem? So let's suppose that you discover that in fact you've checked that out, you found that the OS was struggling, and you fixed it. So why would I say you still shouldn't care? Because there may well be a problem in our process, but not in our code. How could there be a problem in the JVM, but not in our code? What could that be about? This is the next thing to check. Okay, so it's not rocket science. I mean, you won't be surprised. You won't really be surprised when I show you what I'm going to do next. So I've got something called Not Our Code, a program. That's the word I'm looking for. A program called Not Our Code. And I'm going to run this program, and I've turned on garbage collection logs, as one always should. Sorry, if we can see it. So I'm saying I'm going to send the garbage collection logs to a little to a log there, and I set that going, and I'm going to take a look for at a log analyzer just to get a quick look at what's going on. So I've obviously run this in the past. Where's the log analyzer? everything gets rearranged. Here we are. So I'm using something called HPJ meter, which is available for a free download from HP. And I think probably my program will have finished by now. It has done. Let's have a look at the garbage collection logs. Open file. Not my code, GC. Oh dear! So it's saying it can't cope with what I've given it. So HPJ meter is a free tool, and things don't always work quite as well as you'd like with free tools. So it's objecting to the log formats change all the time. But luckily, this one's a pretty simple one to get rid of. So if you were what was it? Minus. If you want to do this kind of thing a bit more seriously, then I would advise you to get a log analyzer which is more competent. There's one called Sensum on the market now, which I just have to advertise. This is because Kirk Pepperdine, who's the guy behind it, is a well-known performance tuning expert. I learned whatever I know about this from him, and he's put all of his wisdom into that. So here is the GC log, and I don't really need to look very far to see that this is in red, and the reason it's in red is because this process is spending 30% of its time in GC, which is ridiculously high. and if we go and look at the heap usage after GC, we can see this is just I can't think of a polite word for it, and I won't say the word that comes into my mind. But what we've got along here is just these are all full GCs. This is a disaster. I mean, the reason it's a disaster is because, of course, I sabotaged the program again in order to make the point. If I go back and look at the VM parameters, then we'll see that what I did was I set the survivor ratio to some ridiculously large number. That means that in effect, I mean, I just completely hosed the garbage collector by saying you're just going to have to promote everything you produce into old space, and that just means it's going to have to do full collections over and over and over again. Again, that's obviously a kind of ridiculous case, but it does tell you, once again, it's another reason, don't turn your profiler on yet. So you probably shouldn't be turning your profiler on at all, but if you must, first of all, make sure because your program's too slow, and that is against a target. Secondly, that it's your process, the JVM, that's the problem, and not the operating system. Thirdly, that if it is in the JVM, that it's not the garbage collector, which is by and large the biggest consumer of CPU time in the JVM anyway. So that's the first place to look. And then only after that should you be looking at your code. Well, let's go on and have a look at some code now. So here I've got no, I don't want to do that. So here I've got before I do that, I'm actually going to show you the program that we're actually going to profile, because this is really we're now really getting back to the question about stream performance. So there could be a problem in our process, but not in the code, because GC is using all the cycles. And there could be a program in the code, but not a stream program, not a stream problem. So let's have a look at the algorithm I'm going to use for doing this grep minus b. I just want to turn off mirroring displays. There we go. Okay, so here's a solution. Here is a solution for grep minus b. And unfortunately, the slide doesn't. I'll have to explain the slide. So the idea is that we're going to look at this. The idea is that we're going to take each line of the input, and we're going to make a partial solution out of it. This is the notion. So the partial solution is going to contain the text of the input. It's going to contain the length of the input, and it's also going to contain the displacement of this component within the partial solution. So this partial solution is just a little one. It's an element. It's all on its own. So its displacement is 0 within that. Here's another partial solution, a bigger one. So this one is still, its displacement is 0. Its length is 44. So the second line of this partial solution, its displacement is 44, because that's how far in the file it is. And so you can see this way, what we can do is we can take each line of the file in turn and merge them together gradually, and eventually we end up and eventually we'll end up by merging the whole lot together. Over here, we've got a partial solution. And again, it's 0 and 40. It's 0 here, a length of 42, so the displacement of the last line is 42 within this partial solution. But when we merge them together, I'll show you how that works in a minute, then the whole thing comes together. So this is a functional star solution. Notice there's no accumulator there, right? So that's good. If you came to my yesterday's talk, you'll understand the next slide, but I'm only going to mention it very briefly. I talked about devising collectors, and I said you need 3 elements to it. A supplier, which produces an empty container, in this case we'll say a list, an accumulator, which adds an element to a container. So this accumulator here takes that line and adds it to the empty container. It makes up this disp line structure and initializes it. And then here comes another accumulator, and it adds that, and it adds another element onto the list. And we've got so we have the first one here and the second one with the displacement in correctly. So these are 2 elements of collectors, as I talked about them yesterday: supplier and accumulator. And now the combiner here comes the combiner. And the way that 2 partial solutions get added together is that you take the length and the displacement of the last element of the left-hand side. You're going to need those because the displacement of the first element of the right-hand side is going to start from the sum of those 2. So here we're saying, well, the total length of the left-hand side is 80, and we can add that to the displacement of each one of the elements of the right-hand side in turn. So and that's how we end up with the right result. So this is a collector solution for grep minus b. Let's have a look at how that works when we try and profile it. Because I've now got to the point where I actually have some code that is really usable-ish. So I'm going to run the profiler on this. I'll switch to NetBeans now because they have a profiler that actually works. Oh, but I haven't mirrored the displays, sorry. Mirror displays. Okay, so this is running. I started the profiler before I mirrored the displays, and you can see that the code here, while it's running, I'll mention here's the code. It's not actually very complicated. The supplier produces a new. For various reasons I didn't use an array list. I used an array deck. So we're creating a new empty container there. For the accumulator, it's a very simple matter of simply taking of adding the new element to the right-hand side of the deck, and then I have to do something clever about getting the displacement right. And the combiner does what I just said. So let's have a look at what happens when we profile this. We'll have a look at the snapshot, and here's the snapshot, and it's spent 26 milliseconds doing this. 26 seconds doing this, and I'm just going to get a very quick look at where it spent most of its time. And we see that it spent its time, kind of understandably enough, in the collect method, because that's most of what there is in the program. We don't actually have any intermediate operations in this program, and basically what it's spending its time doing is the work it's done is in fact the work of the combiner. So the combiner took up almost all the time there. There's something with the accumulator, but almost all with the combiner. Now, you might say, well, that's kind of not in itself. That doesn't tell us very much. Let me see if I can get back to my slides now. So this actually isn't a great. I haven't shown you the bottom. Right. So the problem with this program is that the code is that the problem is not with the stream code, because strictly speaking, the stream code is of what we're looking for parallelization in particular. The problem is going to be we're looking for what's going to be done by the intermediate operations. Here, it's the collect operation that has cost the work. What's wrong with this program is, well, possibly not very much. It actually performs relatively well compared to grep minus b in the Unix code. so the overall performance is comparable to that. But the difficulty is that we can't go parallel with this, which is where we're headed with this stuff. Well, that may be a difficulty and it may not. There are a lot of programs that you don't expect to go parallel with. This one, it would be nice if we could. We're not going to do that because this problem is a so-called prefix sum problem. It's a prefix sum algorithm. Every element of the result is dependent on what went before. and the combiner, therefore, if you think back to what that combiner looked like, basically what it's doing is in order to calculate the new displacements on the right-hand side, it's got to process every element on the right-hand side. So the combiner is going to be order n, at least order n actually. And so that means it's not fit for parallelization. And what's more, by the way, there's a further problem with this in that the input that I was using for it was streaming I/O. I was using the method buffered reader.lines. And essentially, buffered reader.lines is going to feed in the elements. Well, not as in my ridiculous first example, one character at a time, but one line at a time, right? So that's not going to be suitable for parallel processing of lots of lines at once. So a major rule about stream performance is that if you want to go parallel, the workload in the parallel sections has to more than offset the overhead of starting and terminating the streams, and that's not going to be the case here. It's Amdahl's law. So I talked about the good fairy that stood over the shoulder of the microprocessor when it was born. That was Gordon Moore. The wicked fairy was Amdahl. So I always find Amdahl's law so depressing. You can't really clearly make out what this graph says, but it's saying what speed up you're going to get from having multiple processors. If you've got it goes from 0 to 100 here, and it goes from 1 to 100 here for the number of processors. You'd like to get a parallel speed up of 100, a factor of 100, from having 100 simultaneous processors. But you'll only do that if they're all working efficiently in parallel. And if there's a serial section to your code, then that's really going to slow down the amount of speed up that you can get. So what's really depressing about this is the blue line is the ideal, where you've got a totally parallel program. But if you start getting some amount of some serial section to your overall workload, then things get bad. So this line here only goes up to 50%. You're only going to get 50% of the potential improvement you can get, and that's with 1% of serial work in there. If you have something more realistic, say like 10% of your application is serial, then you'll get less than a speed up of less than 10. That's the bottom line. You get a speed up of less than 10 for 100 processors, and in fact, you're wasting your money if you throw more than 15 or 10 or 15 processors at it. So I think this is a very depressing result. But it's inescapable. It's very easy to demonstrate. This is what it's going to be like. So the solution that I just showed you for grep minus b is absolutely not going to work because it's got a serial section at the beginning with streaming I/O, and it's got a serial section at the end with that collector that I showed you, effectively serial, because of this need to process every element for the combiner, every element of the right-hand side. So what about a parallel solution? So the one thing that I haven't talked about so far is the way in which we can feed data into streams in parallel. Parallel streams need splittable sources. This is implemented by a thing called a splitterator. I showed this diagram yesterday. The idea of a splitterator is it takes a data set here and it divides it up repeatedly until it's got a subset of the data that's fit to send into a single thread for processing. And then each thread then works its way along the data set element by element. So this was the splitting part. This is the iteration part. Splitterator. Very cool. Or cute, actually. So in thinking about this problem, I invented something called a line splitterator. Now the key thing about this is there a way in which we could split up this? Imagine it's like a million-line file, and get away from streaming I/O. So actually, I shouldn't have showed you that. what is the way in which we could get I/O without having to stream it? I know it was on the previous slide. I know it was on the next slide, but you can still say it. Sorry?
You're mapping the file with random access.
Pardon?
You mean random access, but you're mapping the file.
Yes, if you map the file, if you put it into a map byte buffer, essentially that allows the operating system, that gives the operating system the possibility of getting a direct correspondence between memory and file store, then effectively you can treat it as a random access. And that's just going to transform things. So the line splitterator that I implemented here goes, the splitterator coverage, that's the data set that this splitterator covers in the first place, is the whole thing. And we take some kind of random midpoint, and we see, well, okay, that's not a suitable place to split it, because clearly that's not going, that we aren't going to get two partial solutions out of that. So what we can do is, if we work our way along to the next new line, right? Then at this point we can now split into two new splitterators. So the old splitterator takes the top half, covers the top half, and the new splitterator covers the bottom half. Sorry? And that's done in memory, yeah, absolutely.
So you're reading the whole thing in memory.
Well, the operating system handles that. I mean, that's the way mapped byte buffers work. Pardon?
The solution has to fit into memory.
It doesn't actually have to fit into memory because of the way that mapped byte buffers work. It's a good question, but I don't really have time to cover it here as to the way that mapped byte buffers manage this. So this is actually a pretty good solution, and the point of showing it is to say, well, you can do a lot better if you think about how are you going to try to eliminate serial parts of your program. Notice that I haven't really spent much time here talking about the intermediate operations. I'll come on to those in a moment. Just to stick to this for a minute, the splitting action of the line splitterator is log n, as you can see, because it's like it's breaking it down in a binary split each time. The collector no longer needs to compute the index. The result, as I found, is relatively independent of data size, and for a sequential stream, it's already better than the iterative solution. So this should make you feel good about using streams anyway, right? Even if you don't think of clever stuff to do with this. And the parallel stream then turns out to be more than 2.5 times as fast as a sequential stream for most data sizes. That's on 4 hardware threads. So we're not getting ideal parallelization, but we're doing pretty well there. And actually, I worked really hard when I was writing the book to try and find an example of a splitterator that wasn't already in the platform classes, because I wanted to demonstrate this is what you would do. And then they looked at this and said, well, we should probably have this in the platform library. But it's still a good example, even if it's from now on, from JDK9, going to be in the platform library. Okay, so now the question that everybody really wants to have answered: when should we go parallel? What are the criteria for going parallel? I mean, by and large, I'm going to say you should, if you're thinking only about sequential streams, you shouldn't worry about performance. Obviously, I'm saying that all the time anyway, but I'm saying that because there are various things that compared to iteration over collections, sequential streams, are going to be, generally speaking, you won't have to think very hard to check that you're going to get this equal or better performance out of going to sequential streams. But what about going parallel? This is what everybody wants to know about. And the answer to that really lies in Amdahl's law again. The workload of the intermediate operations has got to be greater. It's got to be great enough to outweigh the overheads of splitting, of setting up the splitterator, of doing concurrent collection, because one way or another, if you're using parallel streams, then at the end of the stream, they've got to be collected back into a mutable data structure, or else they've got to be accumulated. But usually they're going to be put into a mutable data structure, and somebody's got to manage that. Either you can leave it to the framework to do that, because the framework will do that for parallel streams with you. You can accumulate into an array list or a hash map or something that isn't thread safe, and the framework will manage it for you. Or you can accumulate into a concurrent map, but still that represents an overhead that's got to be managed. And a big deal is initializing the fork join framework. So all this runs within the fork join pool, the common fork join pool, and there's a cost to setting up the tasks that the different threads will actually execute. And this cost is around about 100 microseconds, give or take. I mean, it's not really easy to say. I thought it was less, and the Oracle team thought it was more. So you can take your pick. They thought it was about 2 or 3 times that, and I thought it was about half of that. So this workload of the intermediate operations thing is often quoted as n times q, where n is the size of the data set and q is the processing cost per element. And you've just got to make sure that's high enough to be worth your while going parallel. This is quite hard to know, not because n is hard to tell, but because it's often quite difficult to tell what q is. And that may well be a cause for benchmarking. So I've talked about splitterators and I've talked about collectors. I've talked some about collectors. What about intermediate operations? Mostly intermediate operations they vary very much as to how parallel friendly they are. So things like map and filter, in which the result of the computation only depends on each element individually, are completely parallel friendly. Things like sorted, stateful operations like sorted are just they're a parallel barrier. In order to sort a parallel stream, you're just going to have to accumulate all of the results and sort them. So parallelism will go out of the window while you're doing that. And then there are ones which, sorted is the worst of the stateful ones. And there are those that require ordering that you don't think require ordering. And the best example of that one is limit, which you think is kind of quite painless. Limit just says, oh, I only want the first 20 or 100 or 1,000 elements of this stream. But actually, that's a real killer for parallel processing, because, of course, how can you tell which one's the 20th or the 1,000th if they're all being processed in parallel, and you've no way of telling, between the different streams, you've no way of telling which one is, quote, the first one. So they had a very frustrating time with limit, and it was very, very difficult to implement in parallel. So the intermediate operations that you don't need to care about are mostly the ones you're going to use. So they're going to be things like, non-deterministic ones are good as well. So find any and any match. Those are good as well because there's no ordering implied with them. Collectors are a bit of a problem. They can be a bit of a problem. I was surprised about how much of a problem they were, to be honest. With the simple collectors that just that collect into linear data structures or into sets, the performance for these is usually dominated by the accumulator because you don't have that many combine operations. But for maps, either to map to concurrent map or any of the collectors that the classification collectors, then the problem there is the combiner has to merge maps together. And map merging turns out to be very slow, and especially concurrent map merging. And that is actually the biggest use case for parallel streams. So that's a significant problem that you need to be aware of. And one of the things I found was it makes a really big difference if you are collecting to a big map and you start off with a small one. So the default size of the collections that the collectors start off with are the default creation sizes, which are pretty small. And for a big map, there's going to need to be resized multiple times, and that resizing operation is very expensive. So presizing maps is presizing all data structures, but maps in particular is a really good idea. And finally, there are issues to do with this is all very idealized. What we're talking about here, the things that will work with parallel streams, it's quite a niche case. We're thinking about CPU-bound operations really very much. Intermediate operations that block are going to foul things up because basically they're going to use up threads from the common thread pool that nobody else will then be able to get access to. So this stuff really only works with data sets that can be split easily and with operations that are very CPU intensive, very processor intensive. So, like, you know, if you want to, I'm sure it'd be great for chess programs, and it would be. There's a lot of things that it would be great for. Actually, I shouldn't say it like that's a kind of minor case, but it's still not a kind of it's not a major case. If your intermediate operations are going to need to do database accesses, or they're going to need to go out over the network for something, then probably parallelization isn't going to be a great answer for you. I mean, it's definitely not going to be a great answer for you. And so one aspect of the kind of niche that here is that it's going to work, but only for certain kinds of problems. And the other one is that the environment that your parallel streams are operating in assumes the framework assumes that it's got the processors to itself. So the fork join pool by default, the common fork join pool is sized to have as many threads in it as there are hardware threads on your machine. So that's either the number of cores, or typically on Intel machines it's twice the number of cores. And if somebody else, some other process, or even some other thread pool within the JVM wants its share of those processors, then the fork join pool is not going to be optimally sized, and your programs are going to tread on one another's toes, and that's going to hurt. And that's going to hurt your performance quite a lot. So really, you have to kind of understand the context of how your program's operating, and the nature of the work it's doing. I've suggested in a kind of facetious way to Brian that they've really made parallelism a little bit too easy in the Streams API, because people don't want to think about this. I mean, it's very sexy to be able to use all your cores. I mean, everybody wants to be able to do that. And I think in the future, the technology may well advance further, and it may be a lot easier to do it. But at the moment, that's where we are. I'm not saying you can't do it at all, but I am saying that you have to really think quite hard before you do. So my conclusions are: performance mostly doesn't matter. This is obviously this is the big line of the sermon. But if you absolutely must do it, then sequential streams normally beat iterative ones, iterative solutions. Parallel streams can utilize all the cores, providing you fulfill those criteria. The data has got to be efficiently splittable. You have to think about what you have as your data source. The intermediate operations are sufficiently expensive. That's a weird thing to say, but the Amdahl's law operates. You've got to have enough workload in the parallelizable parts to outweigh the overheads of setting up the parallelization, and you've got to know there isn't big contention for the processors. So that's almost the end. There's some resources here, and needless to say, actually I will, I'm kind of not too diffident about recommending this, because it does have a performance chapter in it. It's not the best performance analysis book in the world, but it says more about performance analysis of streams than anything else that you're going to read. There's a web page that's been set up by Doug Lee, who's the originator of a lot of this stuff, for as guidance as to when you should go parallel. Alexei Shipalev is the main author of the Java benchmarking harness, and I really recommend you to read his stuff. I mean, he's a guru on the subject of benchmarking. So he's got a really good talk here, and he's got and this is where you can go and find JMH to play with. So one last plug. I'm sorry, I just can't resist this. I managed to persuade them to set up a desk where we could sell books. So the book will be on sale from 1 o'clock to 2 o'clock today, outside in the registration. So thank you very much for your attention. Okay, we've got a few minutes for questions, yeah?
Yeah.
So. All right.
All right, so early on, I was a little bit confused when, in the part where you were talking about why we shouldn't care. Because things that were outside the process or not our code were still determined by how we had coded or run the process.
Yeah.
But And I have a little theory. Maybe you meant as far as parallelism is concerned, as opposed to as far as performance is concerned.
Okay, so the question was, so I'll just repeat it. The question was, what did I mean by why we shouldn't care? And yeah, I guess you're probably right. Actually, I did have a longer title to that slide, but it didn't fit on the slide, so I took it off. I didn't mean that we shouldn't ever care about performance. What I meant was we shouldn't care about optimizing particular bits of our Java code. When a program runs slowly, when Java programmers, when their application runs slowly, immediately get the profiler out and start looking to see what's wrong with this particular bit of code. I always knew that was an inefficient way of doing things. And, yeah?
I'm sorry, but then one still needs to fix those things, right? One needs to find and fix them.
No, well, very probably not. If the problem is that you're reading your file input without buffering, then you really shouldn't care about the fact that you've got a variable is being assigned inside a loop when it could be hoisted out of the loop.
Absolutely not. Right.
So maybe I should. Perhaps that was a little bit deceptive. Maybe I should have said, once you've decided that you haven't met your performance target, this is the order in which you should care about things. That would have been a better way of putting it.
So basically, find the bottlenecks first before optimizing.
Absolutely. And it's quite likely that it won't be in your code. And you shouldn't look in your code first. Of course, you should find the bottlenecks, obviously. But the order in which to look is really important. So you don't start looking in your code until you've actually determined it is in your code. And the process that I showed you very, very briefly is a way of narrowing it down. And when I say why you shouldn't care, it's why you shouldn't apply the profiler and why you shouldn't worry about what your Java code is doing until you're really certain that is the problem.
I had a quick question. Your talk assumes that splitting your data source is something that's actually done sequentially before you're actually doing your parallel processing. But I'm less familiar with Java 8 than I do with Spark. And we've been able to make Spark actually do the splitting in parallel too. So is that?
The splitting does happen in parallel. If I could just go back for a minute or two, then go back a bit. Where's it gone? Here we are. I'll get it in a second. Oh, okay, so this slide's not too bad. Right. Okay. So this split here is done by a single thread. A single thread has to split it into this, and then we get two splitterators, and now each one of these things is going to be split. So this will be split by a different thread from the one that splits this one, and now we've got 4 threads. And in each case, the original thread takes the top half of the split and assigns the bottom half of the split to a new thread from the fork join pool.
Okay, you could literally take the file descriptor as the source and immediately go to the parallel processing of 4 threads, because you can actually have each of them independently decide where to split the file. We've actually recently done that for Spark, so that's why. Exactly. You could basically just seek to the right point in the file and move forward or move back.
But how would you know what the right point in the file was?
Because you know what the size is.
Yeah,
It's the only thing you have to do beforehand. I know what the size of the file is. I know I have 4 splits. I know exactly where to break each of the 4 splits.
But you don't if it's a file that consists of lines of variable length.
Actually, you do, because you just have to move to, because each of the pieces could have the same set of rules where they're consistent. So they produce a data set that's exhaustive and mutually exclusive by doing exactly the rule that you talked about, which is move to the next line. Yeah,
so you would do the same thing, but you wouldn't necessarily put it in a mapped byte buffer.
Right, exactly.
First.
You would basically do a random access to the file, find the next line, and that's where you're. Yeah, right. Exactly. And you know where the next one needs to end using the same logic. And all of the splitting is done in the separate threads in parallel prior to actually feeding it to the. And collecting can be done the same way, not necessarily in every case, but for example, if you're collecting to an array. And you know the index of the result, you could, in parallel, write the results into the array. You do have to count them, and in some cases you can, but in some cases you can't.
Okay.
So.
Right. Okay.
Has there been any talk about allowing the JVM to determine whether to run in parallel, like to optimize itself?
Well, I see what you mean. You mean a kind of top-level decision. Yeah. And well, you should read what Doug Lee says in the parallel stream guidance document, because he actually answers that question specifically. Basically, this stuff is too hard for the JVM to decide about. You're bringing too much information from outside of what the JVM can see. You're bringing that to bear on it. I do think that may be an area where they might improve. I mean, one thing that I'd really like to see, I don't know whether it's going to happen or not, one thing I'd really like to see would be some kind of administrative console which would allow you to configure thread pools at a JVM level, but actually at an entire machine level, so that you could actually allocate threads to processors in a more rational way than just assuming that we've got them all, which is the current situation. Okay, no more questions? Thank you very much.